Okay, so lecture 5 is on electromagnetic induction. So we're going to cover Faraday's law, Lenz's law, mutual inductance, self-inductance, and inductors, which brings it back to circuits. So at this point, we know that a magnetic field is just something that's created by moving charge, or in other words, current. We also know that if another charge, separate from that charge that's creating the magnetic field, if that other charge travels through that magnetic field with some velocity and in some orthogonal direction to the field, right? Remember our right-hand rule? Then that charge experiences a force, the magnetic force. If the charge moving through a magnetic field is in the form of a loop or current, then we talked about how that loop of wire, or circuit, I mean, not current, then that loop of wire may experience some net torque and begin to spin about some axis. And we ended talking about a DC motor, and I just think that's the coolest thing ever. So in this lecture, we learn about yet another phenomenon that is the basis for a ton of electrical applications, or electronic device applications, and that is electromagnetic induction. In words, electromagnetic induction is the following. If the magnetic flux through a circuit changes, an EMF and a current are induced in the circuit. So at the heart of this phenomena is Faraday's law, which relates induced EMF, right, a voltage source EMF that is induced on a circuit, induction, same word, right, to changing magnetic flux in any loop. And Lenz's law just kind of simplifies things and tells us the direction of these induced EMFs and current. So in straightforward terms, electromagnetic induction describes how we can move some magnets around in the air near a circuit and get current flowing in that circuit. It's pretty cool. And this works with any conductive loop, and there doesn't need to be any battery or any other EMF source or any other circuit components at all attached to that circuit. You can move a magnet around a ring on your finger in such a way that charges in the ring are induced to move around the ring, just as if you'd cut the ring open and attached either end of the cut ring to the positive and negative terminal of a battery, say. And that would induce charges to move. Well, we can do the same just by waving a magnet around. It's very cool. So this concept is exactly how wireless charging works. Like when you put your phone down on a wireless charging pad, this is how it works, induction. But it turns out also that it goes beyond just wireless charging. It's involved in how almost any electronic thing works, because this principle is how power is safely delivered to your home, to power all of your devices. And after this lecture would be a nice time to go watch a fun YouTube video on Nikola Tesla versus Edison and AC versus DC. It's a really cool story. There's a poor elephant involved. But anyhow, every electronic device operates based on its circuit design, and every circuit needs an EMF source, which is, voltage or potential difference or an electric hill for charges to then flow down. That's what makes a circuit have charges flowing around it. So basically, in oversimplified terms, if it doesn't run on batteries, the EMF source is likely derivative in some way of induction. So we're about to learn about that. So 5.1 is Faraday's law. All right, so yet another thing, right, that's going to help us solve problems. It's going to have some conceptual components for us to understand, and it's going to have some mathematical expression for us to use. This is kind of the pattern. Faraday's law of induction states, in words, that the induced EMF in a closed loop, here I might as well type this, the induced EMF in a closed loop equals the negative of the time rate of change of magnetic flux through that loop. what does that mean? The induced EMF in a closed loop, right? So this induced voltage source, by what I've kind of been loosely saying is just waving magnets around, that EMF that is induced in a closed loop, it's equal to the negative of the time rate of change of magnetic flux through that loop. So we're going to break that down in a bit. But for right now, I'm going to write the mathematical version of this, is that the EMF, which we usually abbreviate with this kind of epsilon-y looking thing, it's really a cursive capital E, is equal to the negative of the time rate of change of magnetic flux. So that's delta magnetic flux divided by delta T. And it's the negative. So it's really important to remember that it's not just the flux that induces an EMF in a circuit, right? So if you have a loop and you have a bar magnet, and this is the north end of the bar magnet, and the bar magnet has some magnetic field that points from north to south, right? This is what we're talking about, magnetic field, and then there's some flux through this surface, right? The amount of stuff going through an area, right? Like wind through a screen door. So magnetic flux is magnetic field penetrating through a surface, and the amount of which, it's not just the fact that there is flux, it has to be changing with respect to time. It has to be changing over time. So if you have this magnet, which does produce a magnetic field, and you have a loop of wire right here nearby, there is magnetic flux, but there is no induced EMF. Not until you take this bar magnet and you move it towards or away or wherever, such that the magnetic flux through this surface is changing with respect to time. So that's a really key concept to keep in mind. All right. So now, maybe understanding that, I'm going to read Faraday's law one more time. The induced EMF in a closed loop equals the negative, and we'll talk about the negative, of the time rate of change of magnetic flux through that loop. That's the concept. That's the concept. All right. So I'm going to describe a simple alternator here. So, debating whether I should draw this or copy it. I'll go ahead and draw it. I think you guys enjoy my pretty pictures. If not, then sorry. Alright, so this is going to be a point A on a circuit. It can look kind of similar to our DC generator, but it serves a different purpose. And then it has this kind of connector point, which we'll call a brush, although it's a metal kind of soft connection, to this kind of loopy thing that connects to another part of a circuit, which has a similar kind of shape. And yeah, I'll do it this way then. And then this one connects to a larger loop. Is that one? No, I think I have to do it the other way. All right. So this goes, has some loop part, and then it comes back through, and then like this. And then that makes contact with another brush here, another connector point. And this goes on and connects to a point B, so there can be, you know, a potential difference across these two. Or we can write like this. So if this is rotating on some axis that doesn't look straight at the moment, but you can pretend it is, and if it's rotating about some axis, let's do the other way, like this, at some angular velocity omega, then we can identify, and if there's a magnetic field, so we're going to just leave out the north and south ends of a magnet that may be producing this field, we're just going to say that the magnetic field is straight across this thing like this. And we'll say that the area vector of this thing, let's see, what one do we want to use? just use this. The area vector of this thing, we'll just say points straight down there. The magnetic flux through the loop here is an angle phi, right? And so if the magnetic field, let's just look at it qualitatively. If the magnetic field is going straight across, right, it's going flat against this thing. So that's like, you know, having a screen door pointed, you know, sidelong into the wind. So there's nothing going through the screen door. And if we were to rotate this 90 degrees, that would produce an angle phi of 180. Then you get the maximum flux, because then it would be rotated such that the flux is going straight through. I don't think that helped. And so we want to come up with a relationship between B and A and the angle phi to describe the flux. We want it to scale as such. And so what this is that, and we need the time rotation angle, the angular velocity involved as well. So what this is flux, magnetic flux of this loop given this magnetic field and this rotation, we can say is B times A times cosine of phi, because if phi is 90 degrees, B and A are perpendicular, right? Then there's no magnetic flux. And so cosine of 90 is 0. Whereas if phi is 0 or 180, then the flux is maximum, and that's when cosine is 1. Cosine of 0 or 180 is 1. And so then you just get the full B times A. Anything in between, and this would be less than 1. It'd be, you know, 0.7 something, for example, or whatever. All right, and then I'll just tell you that we can say that this is B times A times cosine omega t, right? Because this angle corresponds to this angular velocity per time t. And so Faraday's law takes this quantity and a delta t and tells us that the induced EMF in this circuit, which is this guy, right, that I wrote down there, is equal to the negative of delta magnetic flux, so that's a capital phi sub b, over delta t, which would be, you just plug the thing in, so delta of BA cosine omega t divided by delta t. And I'm going to take it one step further with calculus and just tell you what this becomes. Omega BA sine omega t. So that is the induced EMF as a function of time. So basically what we find is that the magnetic flux varies according to a cosine function. And this next part I am going to paste in a visual here. So it varies according to a sine function here. And give me a second and I will paste this in here. Boom. Loading. Okay, here we go. So if we were to plot magnetic flux and the induced EMF, then you would find, right, so up here it gives you, up at the top it gives you the magnetic field is constant throughout, and the loop, seen on end to end, is rotating through time. And you find that both of the magnetic flux and the induced EMF vary according to a trigonometric function, right? One's cosine, one is sine, so they're just offset from each other by a quarter cycle. So alternators are found in cars. That may be where you've heard this word before, in cars, to generate the current for all of the electronic components, like the lights, the buttons, the entertainment center. In a car, however, it's not the loop that rotates with the magnetic field constant. It's the loop that stays the same with an electromagnet that rotates around the loop, which is powered by mechanical connection to the motor. Next, Lenz's law.